Okay, all of these definitions and theorems from 2.4, I just have the pages from the book with me so that we can talk about all these good things and then get as many examples done as we can. This is page 90 in the book. First topic is continuity at a point and on an open interval. Your gut level understanding of continuity is, I can draw this graph without picking up my pencil. But there are functions that may not be continuous over their entire domains, but they're continuous on an open interval. You can at least draw part of the graph without having to pick up your pencil. That's continuity on an open interval. Now, this first figure 2.25 shows 3 different ways that continuity could fail to exist on an open interval. This is the open interval from A to B. Notice that an open interval does not include the endpoints, and an open interval is denoted by using parentheses. Pay attention to what interval notation, when you have parentheses on it, then it's an open interval. The endpoints are not included. When you have brackets on your interval notation, then that's a closed interval and endpoints aren't included. All of these are open intervals from A to B. And in this first illustration, that function is continuous from A to B, except for at the point C. F of C is not defined. If you were graphing that, you'd have to pick up your pencil at C, hop over it, and then continue. So that's one way that continuity can be destroyed if there's a point where the function's not defined. Here's another situation or illustration of a function that's continuous from A to B, except for at some point C, and is discontinuous for a different reason than this was discontinuous. This was discontinuous because the function wasn't defined at C. This function is defined at C. There's the closed dot right there. But the function is not continuous at C because the limit as x approaches C from the left is not the same as the limit as x approaches C from the right. You would have to pick up your pencil there because of that gap. And then the third illustration is discontinuous at C, but again for a different reason than the other two. The first picture wasn't continuous because the function wasn't defined at C. Second picture, the function's defined at C, but the limit is different coming at C from the left than from the right. The third one, well, the function is defined at C. What's the limit as x approaches C from the left? You really can't tell because they're not telling you any tick marks on the y-axis, but the limit does exist at C because y is approaching the same thing from the left as it is from the right, but it's not the same as what the function's defined to be at that point. So right under that picture, you have the 3 scenarios or the 3 problems that destroy continuity at a point C. Either the function's not defined at C, the limit doesn't exist as C because your y's are getting close to one value coming at the left of C, but a different value coming from the right towards C. And then 3, the limit does exist and the function is defined, but those 2 things just aren't the same number. If one of those 3 things happen, then you're going to have to pick up your pencil at C to graph that function. You need to know, because it's on the test, not just because it's on the test, you need to know because you need to know. The conditions for continuity, they're just making sure that the 3 things above don't happen. So the 3 conditions for continuity are as follows. F of C has to be defined. The limit as x approaches C of the function has to exist. And then number 3, the limit has to be the same as the function's defined to be at that point, so that you don't have to pick up your pencil and hop over the point C. A function is continuous on an open interval from A to B if it's continuous at each point in the interval, and a function that's continuous on the entire real line, negative infinity to infinity, you just say it's continuous everywhere. Or you can say, here's how I abbreviate it. It's continuous on the real number system. Y'all told me that, I think Mr. Estep showed my SMHS folks that fancy R for real numbers. If you say continuous on R, I understand that you're saying it's continuous everywhere. I could draw the whole thing without picking up my pencil. All right. Top of page 91, the difference between removable and non-removable discontinuities. Discontinuities can cause a problem in calculus. It can cause us sometimes not to be able to find the derivative. And the derivative is what we want to find most of the time in calculus. But some discontinuities are removable, in other words, fixable. Let's see, if a function is defined on an interval I, except for possibly at some point C, and f is not continuous at C, then it's said to have a discontinuity at C. You go, there's a discontinuity at x equals 2, or there's a discontinuity at x equals 4. Discontinuities fall into two categories, removable and non-removable. A discontinuity at C is called removable if the function can be made continuous by appropriately defining or redefining f of C. In other words, over here in the margin, we have a removable discontinuity. This function is discontinuous at C, but all I would have to do to make it continuous is fill in that dot. If I just defined f of C to be the same thing that limit is, then that function would be continuous on the open interval from A to B. So I say that's a removable discontinuity. I can fix it just by filling in the dot. This is a non-removable discontinuity because there's a bigger problem than just a hole in the graph. You get non-removable discontinuities when the limit's different coming at C from the left than it is coming at C from the right. So here, there's a non-removable discontinuity at 0. You can't draw that entire thing without picking up your pencil, and you can't fix it just by filling in a dot. That's a non-removable discontinuity at 0. This is a removable discontinuity at 1, because if only that dot was filled in, if only f of C was defined, f of 1 was defined, then that would be continuous. Here's a piecewise function. F of h of x equals x plus 1 for all the x's less than or equal to 0. That means up to the y-axis, it's a straight line. H of x equals e to the x for all the x is greater than 0. That means anything past the y-axis, that's your nice exponential curve. The reason there's no discontinuity there is because whether you put 0 into the first part or the second part, you get the same y value, you get 1. So the two pieces of the graph do hook up there, and there's no discontinuity because the graph, the line part, hooks up with the exponential part. And then here's a function that's continuous on its entire line. Sine is continuous from negative infinity to infinity. The existence of a limit. So far we have used the notation, the limit as x approaches C of f of x, and that meant that the y values were approaching the same number from the left as they were from the right, and the limit existed. This is called the two-sided limit because we're approaching C from both sides. Sometimes we need to talk about the one-sided limit. What is y as x approaches C from the right? If I want the limit as x approaches C from the right, then I use this notation. X approaches C with a little plus up there means from the right. And x approaches C with a little minus up there is x approaches C from the left. So if both of those limits exist and are the same number, then we say the two-sided limit exists. We've already said that, we just didn't have notation for it yet. The limit from the left has to be the same as the limit from the right in order for the two-sided limit to exist. All right, definition of continuity on a closed interval. If we're including the endpoints, all this definition says is a function's continuous on a closed interval from A to B using brackets. If it's continuous on the open interval from A to B, and then these two extra conditions are met. These two extra conditions are saying if the limit as x approaches the left endpoint from the right is the same as f of A, and if the limit as x approaches B from the left is the same thing as f of B. In other words, if you could get all the way to the endpoints and include both endpoints without picking up your pencil, then you can say the function's continuous on a closed interval. All right, a few other things I need to point at, and then we can do some examples. Top of page 95. Properties of continuity are about the same as the properties of limits. If you have two functions and each one of them, for each one of them, the limit exists, then the limit exists for their sum, and the limit exists for their product and for their quotient, as long as you're watching out for what makes the denominator 0. The same thing is true if you have two functions that are continuous. If f and g are continuous at some point c, then you still get a continuous function if you multiply f or g by a constant. That's what a scalar is. If you multiply it by a constant, it's still continuous. If you add or subtract two continuous functions, you get a continuous function. If you multiply two continuous functions, you get a continuous function. If you divide two continuous functions, you get a continuous function, as long as you're watching out for what makes the denominator 0. The function's not going to be continuous at whatever makes the denominator 0. Well, one other tiny thing, and we're not really going to use this, but I would feel like a bad person if I didn't tell you. The intermediate value theorem. The intermediate value theorem just says if f is continuous on a closed interval from A to B, and f of A doesn't equal f of B. In other words, these two y values aren't the same. And k is any number between f of A and f of B, then there's at least one number c in the open interval from, closed interval from A to B, such that f of c equals k. You got that? Want to see a picture of it? Picture of it would make it make a lot more sense. Look down at the bottom of the page. Here's an open interval from A to B, such that f of A is not the same as f of B. Those two y values are not the same. If those two y values are not the same, and if there's some value k somewhere in between f of A and f of B, if this is a continuous function, then there's going to be a point where the function attains that value. If I said, I want to know if I can draw this without picking up my pencil right here, well, if the function's continuous all the way from here to here, it has to attain every single y value from here to here. There aren't going to be any gaps in the y values because the function's continuous from here to here. All right, let's see what we do with all that good stuff. First, in 2.4, there are some pictures, some graphs that we just need to interpret. Well, let me put those up here. The book asks you for a parts A, B, and C. I want you to go ahead, if you have your book, go ahead and write a D part in here. I want you to answer one other question. I want you to tell me, in addition to the limit as x approaches C from the right, the limit as x approaches C from the left, If the A and B parts both exist and are the same answer, then the C part exists and is that answer, because the C part's the two-sided limit. I also want you to tell me the function value at C. So here we go. In number 2, C is 2. What's the limit as x, oh, that's actually -2. C is -2. What's the limit of this function as x approaches -2 from the left? -2. The answer to the A part is -2. What's the limit as x approaches -2 from the right? -2. So the answer to the B part is -2. If the answer to the A part is -2 and the answer to the B part is -2, what's the answer to the C part? -2. And then my made up D part, what is f of -2? -2. Because that function is continuous at -2, all 4 of those have the same answer. Anytime you have a function that all 4 of those have the same answer, then the function's continuous at that point. The B part, no, not the B part, number 4. C is -3. What is the limit as x approaches -3 from the left? 3. B part, what's the limit as x approaches -3 from the right? 3. So C part, what's the two-sided limit? 3. My own made-up D part, what is f of -3? Oh, because that's where the closed dot is. So A, B, and C had the same answers there. A and B had the same answers, which means the two-sided limit exists. But D had a different answer, which not only means that the function's discontinuous at -3, it also tells you something about that discontinuity. Is that discontinuity at -3 removable or non-removable? Removable means could be fixed by filling in the dot. Non-removable means could not be fixed by just filling in the dot. Which is it? It could be fixed, it's removable. Just by redefining f of C, by moving that closed dot down here, we could remove that discontinuity. And number 6, the value of C is -1. What's the limit as x approaches -1 from the left? 2. What's the limit as x approaches -1 from the right? 0. So what's the answer to the C part? What's the two-sided limit? It does not exist because the left-hand limit doesn't equal the right-hand limit. And what about my D part? What is f of -1? It's 0. So there's a discontinuity at 0. Is that discontinuity removable or non-removable? It cannot be fixed just by filling in that dot. So that's a non-removable discontinuity. All right, you can interpret graphs correctly. Let's look at some of these 7 through 27. Say, find the limit if it exists. If it does not exist, explain why. Ouch, just bit my cheek. Most of these can be found by direct substitution. If the two-sided limit exists and can be found by direct substitution, then that automatically means both one-sided limits exist. In other words, in number 8, we're looking for the limit as x approaches 2 from the, oh no, I can't read it. Is that a plus or a minus? A minus. So as x approaches 2 from the left, well, you can evaluate that limit, that two-sided limit, at x equals 2 by direct substitution. You just put in a 2 and you get 2/4 or 1/2. If the two-sided limit is 1/2, then the one-sided limit is automatically 1/2. So the answer to number 8 is just 1/2. If you can find the limit as x approaches C, if you can find the two-sided limit, then you don't have to worry about what the one-sided limit is. It's the same answer. Number 10, I think I need to write down. We're looking for the right-hand limit, but if I can find the two-sided limit, then that's what the one-sided limit is as well. Could that limit as x approaches 4 be found by direct substitution? Not as is. Can you think of one of our tools for resolving indeterminate form that would work here? You can simplify that rational expression because you can factor the denominator and are x minus 4 and 4 minus x the same thing? Definitely not. They're not the same, but they are direct opposites of each other. So you can cancel them as long as you leave a -1. That's the limit as x approaches 4 from the right of -1 over x plus 4. Can that limit be found by direct substitution? Yeah, that's -1/8. And if the two-sided limit is -1/8, then the right-hand limit is definitely -1/8. Actually, both limits are -1/8, and that's why the two-sided limit exists.
So if we're doing for like one-sided, it's only one-sided limit, like how do we get it to know?
You see if you can find the two-sided limit, and if you can find the two-sided limit, that's the one-sided limit as well. But we're fixing to see a problem where, well, I can't find the two-sided limit. Can I still find a one-sided limit? We're working our way up to that. Let me ask you something about number 12 without writing it down. I'm not going to do this one, but could the limit as x approaches 4 from the left be found by direct substitution? No? That would give me indeterminate form. Which one of my tricks might work on this? Rationalizing the numerator. Let me just go ahead and say that's going to fix number 12. But number 14 is a guy that we need to think hard about. The limit as x approaches 10 from the right of the absolute value of x minus 10 over x minus 10. We need to think real hard for just a minute about what absolute value actually means. I guess maybe I could have written it before number 14, but this is going to be important, so put a star by it. It's not just important on this problem. The definition of absolute value. It's been a long time since we've actually seen the definition of absolute value. We just go, it's distance, it can never be negative, and that's true. But here's the official definition of the absolute value function. F of x equals the absolute value of x is actually a piecewise function. If you put in a positive number into the absolute value function, what do you get at? The same positive number. If you put in a positive, that means if x is greater than or equal to 0, you get out the same thing you put in. But if you put in a negative number, what do you get out? Not the very same thing that you put in, but the opposite of what you put in. That's the definition of what absolute value means. This piecewise function, this is the restricted domain. As long as you put in a number that's positive or 0, you get out the same thing you put in. But if you put in a negative, you get out the opposite of what you put in. Definition of absolute value. So I'm looking back at number 14. If those absolute values weren't there, that would just be x minus 10 over x minus 10. And what is x minus 10 over x minus 10? 1. If I put anything bigger than 10, I'm just going to get a 1 out of that. Can you try a few numbers and see that that's true? You can't put in a 10, but you can put in an 11, a 12, and a 13, and all of those would just give you 1. What if you put in something smaller than 10? Put in a 9, or a 8, or a 7. What do you get? What? -1. So if you put in anything bigger than 10, you get out a +1. If you put out anything smaller than 10, you get a -1. To find the limit as x approaches 10 from the right, are we putting in numbers that are bigger than 10 or smaller than 10? Tiny bit bigger, what are we going to get out? There's a one-sided limit that exists, even though the two-sided limit would not exist. Let me remind you what this graph would look like. Or let me tell you what this graph would look like. If I put anything, let's go by this definition right here, only instead of bigger than 0, we're saying bigger than 10. If I put in anything bigger than 10, what's y going to equal? 1. So anything from here forever to the right, y is going to equal 1. But if I put anything less than 10, what am I going to get? -1, so an open dot right there, and then shade to the left. That's the graph of absolute value of x minus 10 divided by x minus 10. It's always either -1 or 1. The limit from the right would be +1. The limit from the left would be -1. And what could you say about the two-sided limit? Does not exist. All right, you're going to see this guy some more. You need to make sure you understand this and why that's the graph of that. So if I ask you for the right-hand limit, it's 1. If I ask you for the left-hand limit, it's -1. If I ask you for the two-sided limit, it doesn't exist. Yes, sir. Ooh, yes, thank you. I said I can't let x be 10 because that would make it undefined, but then I closed my dot at 10. So you're racking up some serious bonus points there, buddy. I don't know where you can spend them. I don't know if Amazon takes my bonus points or not. But there should absolutely not be a closed dot on 10 anywhere because I can't let x be 10. All right, you'll see that guy again. We need to move just a little bit more quickly here. So let me say something about number 16. Number 16, when you clean that up, you'll have something you can plug a 0 in, so you don't need to worry about it. You can find the two-sided limit, so the one-sided limit exists. Number 18, this is a parabola, which is continuous everywhere. This is a parabola, which is continuous everywhere. So the only possible discontinuity is where? At x equals what number? The only possible discontinuity is at 3 if those two parabolas don't hook up at 3. So how are you going to find out without graphing? We could absolutely graph it, but without graphing, how could I find if those two parabolas hook up at 3? Plug in 3 into both of them and see if it gives you the same y value. If it gives you the same y value, then the two-sided limit exists. What's this problem actually asking for? Approaching 3 from the left? If I'm approaching 3 from the left, a number's just a little tiny bit smaller than 3, will I plug 3 into the first? That's both-sided? When I printed this yesterday and I could read it, I was wearing glasses. Today with contacts, I'm having a hard time seeing if there's a little plus or minus up in the air. If that's the two-sided limit, then it doesn't exist. Well, it may exist if f of 3, if you get the same y value, if you plug both 3 here and here. I think I need to write this down just to show you the notation. The limit as x approaches 3 of f of x, where f of x is the concave up parabola x squared minus 4x plus 6 for all the x's less than 3, and the concave down parabola negative x squared plus 4x minus 2 for all the x's greater than or equal to 3. The two-sided limit exists if both one-sided limits exist and are the same number. So if the problem asked me for the limit as x approaches 3 from the left, how would I find it? Put 3 into the top function, because if I'm approaching 3 from the net left, that's numbers that are a little bit smaller than 3. So the limit as x approaches 3 of the function would be 3 squared minus 4 times 3 plus 6. 9 minus 12 is negative 3 plus 6 is 3. How would I find the limit as x approaches 3 from the right? Put 3 into the second function, because that number is a tiny bit bigger than 3. Negative 3 squared plus 4 times 3 minus 2. Is that positive 9 or negative 9? That's negative 9, because the negative is not in parentheses. It's not part of the base. Negative 9 plus 12 is 3. 3 minus 2 is 1. My math okay there? Okay. Just checking, never know with context. Might mess up my addition subtraction capability. If I ask you for the left-hand limit, it's what? 3. If I ask you for the right-hand limit, it's 1. If I ask you for the two-sided limit, it does not exist. So it just all depends on what the question is. You have to look carefully to see whether you're being asked for left-hand limit, right-hand limit, or two-sided limit. Doesn't really make sense to say equals does not exist, but it does not exist.
Equals and not exist.
Yeah, that's not okay. That was 18. I'm gonna say 20 is just yuckier because it has a secant in it. That's okay. Change it to a 1 over cosine and think about whether 1 over cosine exists at the half pies. Let's talk about this little guy. Have you seen that symbol? I don't know if it's going to show up good on screen, but it looks like fancy brackets. It looks like that. That is called the greatest integer function. Have you ever seen it before?
I don't remember.
Oh man.
Sounds like on the board once and then never. Sounds like
Okay, so maybe you've heard it before, but it's been a long, long time. Let me, since I don't have the page where that's defined, let me put you another asterisk out here and say this is important. The greatest integer function.
Okay, I ran out of words.
F of x is that wacky symbol around an x returns the greatest integer. That's why it's called the greatest integer function. Less than or equal to x. For example, if I put in a 1.5 then what is the greatest integer less than or equal to 1.5? If I put in a 7, what's the greatest integer less than or equal to 7? If I put in a negative 1.2, what is the greatest integer less than or equal to negative 1.2? Yes, somebody said negative 1. Good. You gotta think on the number line, what's the first integer equal to or to the left of whatever number I put in there. It has the craziest graph ever. Where do you think the discontinuities of that graph are going to be? Where are you going to have to pick up your pencil? Everywhere? Like, if you say pick up everywhere, then I can't even put my pencil down. At every integer. It's going to have a discontinuity at every integer. Do you think that continuity is going to be a removable discontinuity or a non-removable discontinuity? Non-removable. I don't think you're going to be able to fix it just by filling in the circle. So what does it look like? If I put in any number between 0 and 1, what y value is it going to give me? Any number between 0 and 1, not including the 1. It's going to give me a 0. So from the x, or from the origin to here, there's going to be a closed dot on 0 going up to 1, and then an open dot on 1. If I put in any number between 1 and 2, not including the endpoints, what's the function going to give me? The greatest number to the left of or equal to 1.999 would be 1. So you're going to have a closed dot here. It's going to go up there and have an open dot.
Yeah, it's like this way. We call it step.
I started to say it's called the step function. Mr. Estep said square function.
Yeah.
I can take that. That's all right. That's what it looks like. It has non-removable discontinuities. What if I make a deal with you that in tonight's homework, you can abbreviate non-removable discontinuity as NRD, as long as if I ask you to, you could spell it.
That's hilarious.
Will you take that deal?
Absolutely.
All right, I'm gonna make you spell it on the test.
I'm such a crazy.
Maybe that'll be the test. Spell non-removable discontinuity.
Please, make it the
I
test.
will
not fail.
All right, you can call it a nerd
The math people fail. English people succeed.
at each integer.
When has that ever happened in class before? Never. Ever.
So we're not close to number 61 yet, so let's see how we can go into hyperspeed here. Now that you know what, hey folks, please stop talking. Now that you know what the greatest integer function means, I just want you to think hard and see if you can figure out like 21 and 23. You already know what you need to know about natural log, so you should be able to think hard and figure that out. 29 through 32 say discuss the continuity of each function. You just write a sentence. Number 30, what would you say about the continuity of that function in number 30? It's continuous everywhere except for -1, and at -1 there's what kind of discontinuity? A removable discontinuity. That's exactly what you would say. On number 32, what would you say about the continuity of that function? Continuous everywhere except 1, and at 1 there's a nerd. There's an NRD. Continuity on a closed interval. Number 34, semicircle that includes both endpoints? If you were graphing a semicircle from one endpoint to the other endpoint, could you draw the whole thing without picking up your pencil? Yeah, you could get all the way to the endpoint. It's continuous on that entire interval -3 to 3. Number 36, where does that graph have asymptotes? 2 and -2. So what's going to be the continuity from -1 up to 2? Is there going to be anywhere you have to pick your pencil up from -1 up to 2? You're going to have to pick it up at 2, but you're not going to have to pick it up before you get to 2. So could you get all the way to 2 before you had to pick your pencil up? Yes. Yeah. You would just have an open dot on 2 because you couldn't let x be 2. That is a removable discontinuity. A removable discontinuity at 2. 37 through 61. I hope to do a bunch more examples, but I think we've talked about everything. We've talked about absolute value, trig. We've talked about greatest integer function. So those say identify the discontinuities and tell whether they're removable or non-removable. And then the very last, that is the end. It goes up to 61. Hey, do y'all remember a note on the assignment sheet that says all the odd answers can be found at Calc Chat? All right, it says that at the bottom of the syllabus, or not the syllabus, I think it says it in the syllabus and the assignment sheet. If you don't have a solutions manual, you can look at that. Just don't do your homework looking at that. That will not help you. Don't do your homework looking at Calc Chat. All right, start working on that practice test this weekend, because you're not going to be able to do it all Monday night. That would be bad thing. Bad. See ya. No fun this weekend. That's the law.
I'm going to Gallenberg, Miss Mott.
Oh, I'm so sorry. Everybody will be having fun with you. You'll be in Gatlinburg with your calculus book.
You're not wrong. Like the other girls are going to let me sleep.
So we don't come here tomorrow, we go to Stone